It's a little better. All right, so now we've gotten our electrons from row 1. Now we want to jump down to row 2, right? So we're going to go 2s, 2. Then what?
2s6.
2
P6.
2p,
Sorry,
right?
2p6.
No worries. We're jumping across to the p block now. So we have 2p6. This has got to be like the most.
3s2.
Yes, 3. So we're down to row 3 now. 3s2. Now we're in row 3, right? Do we have a D block yet? No,
No.
not yet. So then it would be 3 P 6. Exactly. Now we're in row 4.
4s2.
4s2.
4d10.
Now, D is a weirdo, right? So for D, the block number is always one less than the row that you're in. So if I'm in row 4, I'm going to have which D block?
3.
3, right? So it's kind of a weirdo, Ross. Did you catch that?
Yeah.
Cool. And again, there's a complicated answer to that you don't need to know.
I was about to ask.
Yeah, so there is an answer, but it gets into quantum mechanics and how we number orbitals and things like that. You don't need to know that. Just suffice it to say, D's a weirdo, it's always going to be one less. F is also a weirdo, it's always going to be one less than D, right? But again, you don't need to worry about the D. I mean, the F, rather, sorry.
So if it was in row 5, then it would be 4d10.
Correct. Exactly.
Gotcha.
Yeah. And last but not least, we have
3 P.
this. We're going back to 4, so it'll be 4p3, right? So in the p block, arsenic has 1, 2, 3 electrons. I apologize that you can't see that, but it'll catch up eventually, right? Okay, so did that help Nikki with your question about how to know where electrons are?
Yeah. Also, I think when one of your lectures you went over how on the rows
Yes.
off to the side there's like an 8, an 18.
So I wouldn't want you to memorize that, right? Because you don't need to. So the easier way to think about that, instead of trying to memorize how many are in each row, you can literally count across, right? Row 1 has 1, 2 electrons, right? So counting the boxes, right? Row 2 has 1, 2, 3, 4, 5, 6, 7, 8, right? Does that make sense?
Okay, so for something like fluorurium, would we go up to radon and say 86 core electrons?
I'm sorry, you're looking at number 114 there at the very bottom there?
Yes.
So when you get into row 6 and 7, you have 14 extra electrons from the F block, right?
Oh.
Yeah, so that's where things get weird. So fortunately for us, we don't really deal too much with row 6 and 7, right?
Okay,
so
good.
I'm not going to test you on whether or not you know the F block stuff, okay? But yeah, that is where it gets a little confusing, for sure. But other than that, you're comfortable with how to interpret the periodic table so far?
Yes, thank you.
Yeah. Okay, so now we said we have 18 core electrons, right? What part of our electron configuration tells us about the core electrons?
The fourth row.
So everything before row 4. Yeah, exactly. Right? And what do we say this electron configuration, who do we say that belongs to?
The noble gas of the previous row.
That's right, the noble gas from the previous row. So we can abbreviate our electron configuration by putting argon as a stand-in, right? So argon represents our 18 core electrons. And then we can rewrite our valence as such. Now there was a couple of questions that I saw on our Discord about whether or not you should write them in this order particularly. I'm not super hard line about the order in which you write these numbers. I personally like to write them as they come on the periodic table visually, so S, then D, then P, right? But you'll see them written in multiple ways. So you'll see sometimes online they'll put the 3D orbital first because it's a lower number. That gets into the specific energies associated with all of these beyond the scope of what we need to understand, right? So as long as you have all of the valence electrons represented in their correct orbitals, I don't care what order they come in. Does that make sense? Everybody all right with me on that? Hopefully I didn't confuse you more.
Just think that if we do not put him in that order, it would make it a lot more confusing.
I think so too, but I think some other people were looking at other internet sources for problems and finding that there are some other sources that will do this differently, right? So just so you're not totally confused by that and thinking that you're doing something wrong, it's okay, right? Yeah. Oops. Okay, so how are we doing with electron configurations? We're all right with that? I legit don't know how this happens. Somehow I just got a drawing on my screen. All right. Any other questions about electron configuration? We're doing all right with that? I'm sorry, I haven't been checking the chat.
Yeah, someone just asked if they can see another example.
I'm going to go ahead and skip that just because there are other examples that you can look to in the previous lecture. But is there anything conceptually about what we just did that you're not tracking with? We're okay. Cool. So I do want to move on and get into chapter 3. So chapter 3 is when we start talking about ions and bonding. Okay. So specifically, we talked a lot about the periodic table in chapter 2 and how the characteristics of an element can tell you about how it will like to behave, right? Specifically in terms of the electrons, because the electrons are telling the story for us, for the most part. Whenever we're talking about chemical reactivity, we're talking about electrons. Are they being shared? Are they being exchanged? Etc., right? So we said that metals, which make up the vast majority of the periodic table, right? What do they like to do with electrons?
Like to lose electrons?
They like to lose electrons, right? Everybody okay with that? Perfect. So then if a nonmetal is essentially the opposite of a metal, right? What do nonmetals like to do in terms of electrons?
They gain electrons.
They like
easily.
to gain electrons, exactly. How about the metalloids?
It can go either way.
They can go both ways, right? So they can gain or they can lose, right? Depending on who they're hooked up with, right? So when we talk about the ability to lose an electron, we're talking about the ionization energy, which is essentially the energetic, I'm going to abbreviate energy from now on because I don't want to write the whole word and I'm lazy. So we're talking about the energy associated with losing an electron. Okay. So when we talk about ability to lose electrons, right? What do you think happens as we go across the periodic table? Would it become easier or harder to lose an electron?
It should become harder.
There's more valence electrons.
There are more valence electrons, right? But just knowing what you know about the metals being on this side, right? And the nonmetals being on the other side.
Yeah, that makes sense.
Right. So as we go across the periodic table, they're actually holding on to their electrons more tightly, right? So they're holding on to their electrons more tightly. What does that mean is happening to the ionization energy?
It decreases.
It
Decrease.
does it
That's more positive.
does it decrease?
Decrease.
It increases, right? So if this is the energy associated with losing an electron, right? And we said that nonmetals do not want to lose electrons, right? So when we talk about that want characteristic, what we're really talking about is energy, right? We're talking about how much energy does it take to lose an electron, right? And if you're a nonmetal, it's going to take a lot more energy, right? So as we go across the periodic table from left to right, the ionization energy increases. Okay? Everybody okay with my abbreviations there? IE is ionization energy. Cool. So, I think that one's relatively intuitive. As we go down the periodic table, right, we get more and more valence electrons, right? Everybody, or not more and more valence electrons, more and more total electrons, sorry. Everybody all right with that? So the more total electrons we have, the bigger the atom. The bigger the atom, the easier it is to get rid of electrons, right? Everybody okay with me on that? So bigger means easier to lose electrons. So who would have the easiest time getting rid of an electron looking at the periodic table?
It'd be hydrogen.
So hydrogen has the least, right? Has the least number of total electrons that you can have over here. So that one's going to be held on really tightly, right? What holds electrons on to an atom?
Protons.
Yeah, so we have a positive charge in the nucleus, right? And we have these negative charges that are whizzing around outside. Those negative charges are attracted to the positive charge, right? So that attraction, when it's just one-on-one, is actually much stronger. As you go through and you get bigger and bigger atoms, right? You get more and more protons, more and more electrons. The outermost electrons, or the valence electrons, actually become less tightly bound, right? They feel less of that positive charge from the nucleus. So, which one of these elements would be the easiest to get an electron away from?
Francium.
118. Francium.
Francium, yeah, exactly. Technically, francium is radioactive, so it doesn't actually exist in the real world. And if you're wondering how I know that, anytime you see an atomic weight in parentheses, that's an indication that you're dealing with something that's radioactive, right? So you see how this whole bottom row has its atomic weight in parentheses? All those guys are radioactive, right? So technically, cesium would have the lowest ionization energy, right? So, ionization energy, as we go down the periodic table, decreases, right? Everybody cool with me on that? Questions? We're okay.
Sorry, could you just clarify, like, ionization energy?
Mm-hmm.
Yeah, could you just clarify that? I'm a little confused.
So it's the energy associated with losing an electron, right? So if you have an atom and it's neutral, right, there's always going to be some energetic cost to messing with that, right? Does that make sense?
Yeah, I'm just wondering why, like, if the ionization energy increases,
Mhm.
why does that make it easier to lose an electron? Because
It doesn't.
I would think that would make it harder.
It does.
Oh.
Right? So here, as we go down the periodic table, ionization energy is decreasing. Right? Decreasing.
I see. Okay.
Right? Here, as we go across, the ionization energy is increasing.
I see.
Cool,
Okay.
cool. Yeah,
Yeah,
and I would just advise you guys generally not to try and memorize these trends, right? I think it's much easier to understand why this is happening and then be able to rationalize that, okay? Does that make sense? So I think a lot of students' inclination is, okay, I'm going to memorize how all these trends work. I don't think that's helpful. I think it's much, much more helpful if you understand why those trends are, right? So going from the bottom left part of the periodic table up diagonally, right? The ionization energy is increasing.
When you say increasing, you mean it's really easy to lose an electron?
No, I mean the opposite of that. So, ionization energy is the penalty, right? That's the cost of doing this thing, right? So you can always think of energy as being a cost, right? We're either gaining or losing energy. And when we lose energy, right, that's that means that we've had to give it away, right? When we gain energy, or when we lower our overall energy, right, then that's when we're happier, right? Our costs are lower, everything's easier. Does that kind of make sense? So you can think about ionization energy in terms of like how much it costs to get rid of an electron, right? Other questions about that? Cool. And just for your guys' own edification, Chapter 2 technically has this information, but I think it makes more sense in the context of Chapter 3, so I put it in there, just so you guys aren't totally, completely confused. Everybody okay with ionization energy?
Yep.
Cool. So, that's looking at how much it costs to lose an electron. The next thing we want to talk about is electron affinity. Okay, and again, I'm lazy. What do I do with this? Right, so electron affinity, EA. What do you think that means? What does affinity mean?
Sounds like it goes for a long time. Or
Not infinity, affinity.
Attraction to?
Attraction to, right? So it's a liking of, right? So this is exactly what it sounds like, right? It's how much do elements like their electrons, essentially, right? How attached to them are they? Does that make sense?
Could you repeat that? I was looking at my spelling and I missed it.
No problem. So we're talking about how much an element likes its electrons, right? So how much it likes its electrons, right? Another way of saying that is how attached they are to their electrons, right? So, knowing that electron affinity is about how much they like their electrons, right? Who do you think has more electron affinity, metals or nonmetals?
non-metal.
Nonmetals, absolutely, right? Does that make sense, guys?
Okay, yeah.
Questions?
Wouldn't that be just the exact opposite of ionization energy?
We're getting there, yeah. So okay, if we're going from metals over here across to the nonmetals, right? What do you think is going to happen to the the electron affinity?
And increase.
It's going to increase, exactly. Right? So as you go across the periodic table, electron affinity increases, right? Knowing what we know about ionization energy, right? We know that ionization energy decreases as we go down the periodic table, right? So what do you think happens to electron affinity?
Going down.
Yeah, exactly, right? So as you go down the periodic table, right, the EA also decreases. So, which element would have the highest electron affinity?
Helium.
So you think helium or neon, and that's kind of true, but the noble gases don't really count in terms of these trends, because they don't want to ever give away any electrons, right? So that's an important point to bring down. So the noble gases.
Fluorine?
It would be fluorine. Yes, it would be fluorine. But again, the noble gases don't ever want to let go of electrons. They're not interested in sharing. They want to keep their electrons, okay? So when we're talking about exchange or the ability to gain or lose electrons, we're never talking about the noble gases, okay?
So column 18 would be obsolete.
Pretty much, yeah. Yeah. So as we go from this bottom corner up, we have the electron affinity increases. Right? Everybody all right with me there? Any questions?
So the affinity is just how much it doesn't like want to lose an electron?
Basically, yeah. Yeah.
Okay.
Yeah, so it trends the same way as the ionization energy, right? So you can think about them as being two sides of the same coin, right? It's just looking at, one's looking at how much it takes to lose electrons, and the other one's looking at how much it likes electrons, right? Cool. Questions about that? Excellent. So we already kind of talked about the next one, which is the atomic size. Whoops. Totally unnecessary. I'm sorry, you guys. I just really needed that to be better. Okay, so atomic size. So we kind of already talked about what happens to, oh, this is also known as atomic radii. So atomic size or atomic radii. We're talking about a radius, right? That's looking at half the diameter, right? So and the diameter is just, if I have any kind of spherical object, right? The diameter would be half. That would be the distance from one end of the circle to the other. I don't know why I'm doing it like that when I could just do it like this. That's the diameter, right? So the radius is just half of that, right? So that's telling us about the atomic size, aka the atomic radii. So what did we say happens to atomic radii as we go down the periodic table? I'm sorry, what was that?
Increases?
It increases, right? So atomic radii, because I'm very lazy, are going to increase as we go down the periodic table, right? Why?
Because it has more energy level, so it's just expanding.
So you've got more protons, you've got more electrons, you've got more neutrons, right? You're getting bigger, okay? Now that's going to make what I'm going to say next very annoying. What do you think happens as you go across the periodic table?
Decrease.
Only because I said it like that, right? So it does decrease, right? I think intuitively you'd be thinking that you're still increasing the number of protons and electrons as you go across the periodic table, right? So why wouldn't the radius also increase, right? Hopefully you guys thought that. Yeah? So, no, okay. But now maybe you're thinking it because I said it. So the atomic radius as you go across the periodic table actually shrinks because you have more valence electrons and more positive charge in the nucleus. And so what happens is those valence electrons get held on to more and more tightly, right? The more tightly the electrons are held on to, the smaller the atomic radius, right? So if your electron affinity is increasing, right, then another way of saying that is that you're holding on to your electrons more tightly. Does that make sense, guys?
Now it does.
Cool. So if you're holding on to your electrons more tightly, your atomic radius will be smaller, right? So, atomic radii. Who would be the smallest on the periodic table? Without including hydrogen.
Fluorine.
Fluorine, right? So we'd start up over here, right? And our atomic radius increases. Okay? Sorry, not AK, AR.
Is this another case where we don't include the noble gases?
Correct. Yes, noble gases are always weirdos in some way or another.
Thank you.
Yeah. So what actually happens on the periodic table in terms of atomic size, and I'll show you a pretty picture of this in just a second, is it decreases as you go across all the way until you get to the noble gases, and then you get to this what I like to call a happy place, where you kind of breathe a sigh of relief, and you're comfortable with the number of electrons that you have in your valence, and so you let them out a little bit, if that makes sense, right? Questions?
So the way you wrote it down is that it's going across, well, not across, from the bottom, the last line that you drew.
Yes.
That increases.
Oh, I'm sorry. Yes, yeah. So the atomic radii increase as you go diagonally from right to left, right? You could also think of this if you want to change the direction of the arrow, right? As decreasing.
Oh, that's what I was looking at.
Yep, that's fine. Either way, those mean the same thing. So whatever makes more sense to you, right? Cool. So the last one that we want to talk about is what's known as metallic characteristic. So metallic characteristic is exactly what it sounds like. How metal are the elements. Right? So, what did we say characterizes a metal more than anything?
There's solids except mercury.
No. Negative charge.
Oh.
What do metals like to do?
Lose electrons?
Lose electrons, right? Metals like to lose electrons. So, if being a metal is all about losing electrons, right? And we know that as you go down the periodic table, what happens to the cost of getting rid of an electron?
Decreases.
It decreases, right? So what happens to metallic characteristic as you go down the periodic table? Do you get more or less metal? More, yeah. So if being able to lose an electron is what makes you metal, right? Then being really good at losing electrons would make you more metal, right? Does that make sense? So as the ionization energy decreases, the metallic characteristic increases, right? What do you think happens as you go across the periodic table?
Metallic characteristic decreases?
Absolutely. Metallic characteristic decreases, right? You're going from metals into non-metal territory, right? So it would stand to reason that you're getting less metallic as you go across the periodic table, right? So, you guys like all the arrows to point the same way? We can do it that way. So as we go from the bottom corner of the periodic table on the left, up, metallic characteristic decreases. Okay? Everybody comfortable with that? I think, so these are all known as periodic trends, what we've been talking about today, which are essentially how can we look at the information that's on the periodic table and what it tells us about behavior of a particular element, right? So in terms of behavior, what we're always talking about are electrons, right? So we're talking about what your relationship is as an element to your electrons, right? Everybody comfortable with that? This is probably the most important thing that we've talked about so far, okay? This idea of how an element is defined by its relationship with its electrons. Does it want to lose them? Does it want to gain them? Is it good at losing them, or is it difficult for them to lose, right? So again, I don't recommend memorizing these periodic trends. I think it's much more helpful if you can understand why they exist, right? There is a beautiful summary table of this information in the chapter 2.2, Key Terms and Definitions. There's a lovely diagram. If you were to Google periodic trends, you would be able to find infinity number of these types of diagrams, right? So, but again, I think it's helpful to understand, not to memorize. Coolsies? May I erase? All right? Cool. Okay. So, next thing we want to talk about is losing, oops, try that again. Losing electrons or gaining electrons, right? So if we're losing or we're gaining electrons, right, then we must be going from a neutral atom to an ion, exactly, right? So if we're losing electrons, right, what kind of charge are we going to end up with?
Positive.
Positive charge, right? What kind of ion do we call that?
Cation.
Cation, right? And again, that's positive, right? Paws like a kitty cat. If we're gaining electrons, what kind of ion are we forming?
Anion.
Anions. Right? Again, I think anti, right? As in negative. Okay?
Sorry, what's the name for a positively charged ion again?
Cation. Right up there.
Thank you.
Mm-hmm. And the negatively charged is anion, right? And we said, who likes to lose electrons?
Metal.
Metals, right? Who likes to gain electrons?
Non-metals.
That's right. So, and this seems like a really trivial point, but it's so super important. will metals ever form anions?
I don't think so.
No. For the most part, and when I say for the most part, I mean actually all of them do not. The only thing that's a little weird is hydrogen gets placed over here, making it look like it's a metal, but it can also be a non-metal, so it can behave both as a metal and as a non-metal. Okay, so that's the only weirdo here. But other than that, if you're a metal, you like to lose electrons, right? Which means you're always going to form cations.
So is hydrogen a metalloid?
It's not technically. It's technically part of the non-metals. So if you look at the coloration here, it's technically given as a non-metal, right? But I would say in terms of behavior, because it's so small, it can do some things that other elements can't. So again, it just tends to be a little bit weird. Yeah.
Why is it not liquid?
Because it's super small. We'll talk about more of that in chapter 8 when we get into solids, liquids, and gases. Yeah, it's a great question though. Okay, so when we're talking about losing or gaining electrons, are we talking about core electrons or valence electrons? Valence electrons, right? So this is super important. When we're talking about ions, we are almost never talking about taking or adding core electrons, okay? The reason being is because the energetic cost associated with taking those core electrons is crazy high, right? So the only places that you'd have that kind of energy would be places like a star, right? In the center of the sun, there's enough heat and energy, right, that you can get these weird flavors of ions where you've lost all of your total electrons, right? Something like that, something crazy. But those kinds of conditions don't exist pretty much anywhere on Earth, for the most part, right? So when we're talking about gaining or losing electrons, we're almost always talking about valence electrons, right? So, here's where we connect the dots of our electron configuration, right? So let's look at potassium, K, and let's do the abbreviated electron configuration.
Argon.
So we've got argon, right?
Or S1.
4s1. How did you know that it only has one valence electron?
First row.
Exactly that, right? Because it's in the first column, or the first group, right? Group 1 will always have one valence electron, right? Everybody okay with me? So, if it only has one valence electron, how many electrons can it lose?
One.
Just one, exactly, right? So, if potassium loses this electron, right, what's its charge?
Positive.
Positive. So again, our ionic notation, we write the symbol and the charge as a superscript. Sorry, the lag is so bad. So now the electron configuration for potassium would be still argon and 4s0, right? Do you have to write the 4s0? No. right? I personally think it's helpful because we're talking about an ion, and knowing that it lost an electron in its valence is part of understanding its character. Does that make sense? Kind of, sort of? But basically, what we're saying is that potassium has the same electron configuration, the potassium ion has the same electron configuration as the noble gas argon, right? So we talk about the noble gas electron configuration for main group, elements. I know I'm going off the board here, sorry guys. Oh my god, the lag is so bad. There we go. Okay, so we talk about the noble gas electron configuration, right? We're saying that if you lose electrons and you end up with just a noble gas electron configuration left over, right? Then you effectively have the same electron configuration as the noble gas, right? Does that mean you have the same element? It's still potassium, because what defines the element?
Protons. The protons.
Protons, not the electrons, right? So it's really important to make that distinction, right? The number of protons is what determines the element, not the number of electrons. So even though we're talking about noble gas electron configuration, right? We're talking about only the electrons, right? Everybody with me? Cool. And I threw in another thing here where I said main group elements, just so you guys know. Main group is pretty much anybody on the periodic table that is in the S block or the P block. I have my periodic table up here, but the lag is so bad that you can't see it yet. So eventually I will point out what I'm talking about. Maybe 100 years from now. Cool. So we have the group 1 and group 2 have are our S block, right? So those are main group elements. And then we have over here our P block guys are also main group elements, right? Now the reason why we make that distinction is because these guys here in the middle, the transition metals, because they have those d electrons, they can do some funky biz in terms of how many electrons they can lose or gain, because they're not usually getting back to the noble gas configuration, right? Unless you're talking about the first few, like scandium, titanium, yttrium, zirconium, right? Those guys might be able to form ions where they get back to noble gas configuration, but most of these guys on the higher side of electrons are not ever going to be able to get back to noble gas configuration. Does that make sense, guys? I apologize that the recording is so far off from what we're talking about. Questions?
Can you repeat that last part?
So when you're talking about the transition metals, because you have a bunch of D block elements, you're not going to be able to get back to noble gas configuration, right? So you're always going to be having some valence electrons left over. Does that kind of make sense? So really, when we're talking about getting to noble gas configuration, electron configuration, group 1 and 2 can do this. I wrote that down, but you can't see it yet. But hopefully soon you will. Isn't it fun teaching on the internet?
So you said the main groups are mainly S block and P block.
Mainly, yes. Cool. So if you're in group 1, how many valence electrons do you have to lose?
2.
1, right? So if you're in group 1, you have 1 valence electron you can use. So what type of cation, what charge does your cation always have if you're in group 1? Positive 1, right? So everybody in group 1 makes a positive 1 cation. I have a periodic table up that I'm trying to show you, and it's taking 1,000 years, and I'm sorry. I wonder how this looks on the video. If they're like, what are you talking about after the fact? So, lithium will always form what flavor of ion? What would the ionic notation be? Lithium.
+1.
+1, exactly. How about sodium?
Na+1.
Na+1. We said potassium.
K+1.
K+1. Rubidium.
Rb+1.
Rb+1. Cesium.
Cs+1.
Cs+1, right?
I know you're saying +1, but it's just the plus sign, right?
Yeah, we don't write the 1, but if you did, I wouldn't mark you off for it. Does that make sense?
Yes, thank you.
Yeah. So, we're lazy. We try and write as little as possible, but if it helps you to put the 1 there, do it. I'm fine with that. So, if everybody in group 1 makes a +1 ion, what do you think happens? Can you guys still see me? It's telling me my internet is unstable.
No, I think she froze. No.
Did I froze?
Good. No, you're back.
Okay, cool. Cool. So if group 1 always forms a +1 ion, right? What do you think group 2 always forms?
+2.
+2, exactly, right? Has 2 valence electrons that it can lose to get back to noble gas configuration, right? So, we had Be 2+, Mg 2+, right? What's next? Calcium 2+, strontium 2+,
Barium.
and barium 2+, right? So if you're in group 2, you can form a positive 2 charge, right? Everybody okay with me on that?
So far.
Cool. That's as good as I can ask for. Okay, so we talked about losing electrons, right? Now let's talk about gaining electrons. So who likes to gain electrons?
Non-metal.
Non-metals, definitely, right? So of our non-metals, right, we only have this little triangle here. There's not a whole lot of them, right? When we're talking about gaining electrons, we're always talking about trying to gain enough electrons to get to the noble gas electron configuration, right? Sorry, guys. So, one of the examples
sort
on...
of the most amount of electrons we can gain given any row?
That's correct, right? Because we can only fill out the valence. We can't jump to a new row.
Yes,
Yeah.
That makes sense. Thank you.
Totally. So if I'm talking about fluorine, right? How many electrons do I need to gain to get to noble gas electron configuration? 1, right? So if I look at the electron configuration for fluorine, right? I have helium as my abbreviation. It's not much of an abbreviation at this point. I have 2s2, 2p, p5, right? And what's the maximum number of electrons I can have in the p orbital? 6. Exactly, 6, right? So if I add one more electron, right? Oops. Then I would be adding it to that p orbital, right? Whose electron configuration is this?
Neon.
Neon, exactly. Does that make sense, guys? So, fluorine forms an ion with a -1 charge, right? How about chlorine? What do you think? Same, absolutely, right? It has the same number of valence electrons, right? So it will gain the same number of valence electrons to form an anion. Does that make sense, guys? And what would its noble gas configuration be?
Any? Neon?
As an ion, right? Now it has the electron configuration of argon, right? Because it's jumping from where it is here in valence electrons to the noble gas. Does that make sense? So again, there's 2 ways to think about this. You can think about it in terms of the electron configuration, or you can just visually look at the periodic table and count how far away from the noble gas you are, right? So if I'm at fluorine, I only need to gain 1 electron to get to that noble gas, right? How many electrons does oxygen need to gain?
2.
2, exactly, right? So, what would the ion be that oxygen forms?
-2.
Yeah, you got it, right? O2 minus. How about nitrogen?
N3 minus.
You got it. How about sulfur?
S2 minus.
You got it. It's right below oxygen, right? So it has the same number of valence electrons as oxygen, which means it's going to need to gain 2 to get to the noble gas electron configuration. What about phosphorus?
3.
Exactly. You got it, guys. Now you know how ions are formed, right? Main group elements can only form one type of ion, okay? So you will never have oxygen -1. You'll never have nitrogen -1 or -2, right? You'll only ever have nitrogen -3, right? Or oxygen -2. Does that make sense, guys?
So when gases are losing electrons, they either don't lose electrons or they lose the amount of electrons that get them to the noble gas electron configuration?
Correct, for main group elements, right?
Perfect, thank you.
Yep, exactly. So the last thing that I want to talk about is how we name ions, okay? So when we're talking about nonmetal ions, which nonmetals are always going to form what flavor of ion?
What was it, Dave?
Nonmetals?
Anion.
Anions.
Anion.
Always anions, right? So we have the nonmetal name. So for anions, we have the nonmetal name. But we get rid of the ending and we add an "ide" to the end, okay? Now where you get rid of the end, what part of it you truncate is kind of weird for these guys, but because they're so commonly used, most of you guys probably already know them, right? So if we're talking about the fluorine anion, right? What's that called?
Chloride.
Fluoride, exactly, right? How about the chlorine anion?
Chloride.
Chloride. What about this guy? Oxide, exactly, right? How about this guy?
Nitride.
Nitride, right? So if it sounds right, it's probably right. Does that make sense? Because we use so many of these in common parlance, right? Carbon dioxide, right? We use these pretty frequently, so you've seen them before. So if it sounds weird, it's probably wrong, right? What do you think this one is?
Sulfide.
Sulfide, exactly. So I think those are relatively intuitive. The main thing and the most important thing to remember is that when you see the "ide," that's an indication that you're talking about the anionic form, right? Not the regular nonmetal atomic form, okay? Now for cations, they're even easier. When you're talking about main group metals, all you do is take the metal name and add ion to the end, right? So if you're talking about sodium, it would be the sodium ion, right? If you're talking about magnesium, it would be the magnesium ion. Does that make sense, guys? Everybody all right with me there? Cool. So again, the most important thing when we're talking about how to name stuff is remembering what the name tells you about the structure. Shush, you.
Every time I see that, I think it's mine.
You're like, oh no, I gotta plug in. That's funny. So the most important thing about the name is, again, remembering what it's telling you about the structure. Now, why is that important? Can I erase, guys? We're okay? So why is that important? Right? So here I have two extremely different things, okay? They're both sodium, right? But this one over here is a sodium atom, right? And this one over here is a sodium ion, right? Do we eat sodium?
Yes.
Which one of these do we eat? the ion, right? So we eat this, we need it to live. Literally, we would die if we didn't have sodium. If you have too much, you'll also die, right? But this is a required part of our diet, right? What happens if you eat this guy? Anybody want to guess?
I'm
I
gonna
don't
guess
know
that
for a fact, but yeah.
What?
Sorry, you go ahead.
Sorry. I was gonna guess that it could be poisonous, like for our body. Like it's just not healthy.
It's better than not poisonous. It explodes
That's even worse.
on contact with water, right?
Oh, that's right. That's right.
Yeah. So, if it explodes upon contact with water, and you are mostly made of water, then if you put this into your mouth, you will die, right? So, I think a lot of students become annoyed by the names and the symbols, right? I wrote Na. Why does it matter if I have the plus sign there? It doesn't seem that important to me. This is the example that I want you guys to think about, right? Of why it is so important to write the plus sign and not write the plus sign, because they mean very, very different things, right? One of them we can eat. The other one will literally kill us, right? So it's... Go ahead.
Sorry. The reason we can eat the ion and not the anion is because the ion is already bound to something, probably like a halogen or something, to form what we would call salt.
So that's what we're going to get to tomorrow on Tuesday. Just a brief reminder, guys, that Tuesday morning we're going to have the lecture for Wednesday. If you want to come, cool. If you can't, totally fine. But it's not about being bound to someone else. The sodium ion is happier because it doesn't have that extra electron, right? It has a noble gas configuration. So even though it's carrying a charge, right, it's still happier in an environment that's surrounded by water than sodium atoms are, right? Because sodium atoms hanging out with water, that water wants to snatch electrons from it, and sodium wants to give them away, right? And that reaction is violent. Okay?
What time is the lecture tomorrow?